Hello, everyone. All right, can I have your attention back here in the class? Thank you. All right, so let's continue with the discussion from Monday. On Monday, we got ourselves an equation, which we call it the wave equation, or 1D wave equation. For some people, they just simply call it a string equation. And this is what we have to solve. We have the constant C, which we define it as C squared T over M. This is from last lecture. So we realize that this is a PDE and not an ODE. This is a partial differential equation. All right. And there are some headaches solving this equation. But we will try to solve it with the same method that we had before. So we started by saying that maybe y, x, and t, because remember now the solution is function of displacement x and time t. We decided to go with yx cosine omega t as just a guess to see how it works. Obviously, we need to take the derivatives, which we did last time. Derivative of y with respect to t gives me minus y omega squared cosine omega t, and derivative of y with respect to x, of course, partial derivative, it gives me derivative of y with respect to x cosine omega t. And I emphasized last day that when we take the partial derivative, we will use the sign for partial derivative, and when it is only one variable, which is the scenario here for yx, the capital Yx, we don't need to use the partial derivative because it is just function of one thing. We substitute these things in the equations. Let's do it again as a recap. So we will get c squared d2y dx squared is equal to minus y omega squared cosine omega t, and obviously cosine omega t on this side as well. So I have cosine omega t and this one. So let's simplify this equation. We will get d2y over dx squared plus omega divided by c squared y equal to 0. Right. So now this is an ODE. It is just depends on one variable. So this is an ODE, and we know how to solve ODEs. So in fact, what we did, we separate the variable time, right? So now let's try solving this equation. This is a simple ODE, and probably we know how to solve it. Again, we start with a guess solution. Let's say yx to be equal to a sine, I'm out of letters, maybe kx. That's again a guess to solve this ODE. Like always, we need to take the derivatives. Let's do that. d2y over dx squared. It gives me minus a k squared sine kx. Substitute it there. It will be a k squared omega c and sine kx equal to 0. So a cannot be 0, sine kx is a sinusoidal. We have to set the one in the bracket equal to 0. Therefore, k is equal to omega over c. So what we found that then yx is equal to a sine, replace k omega x over c. All right. So now what I need is some extra information. I can rely on boundary conditions. We need boundary conditions. Always when we solve ODE and PDE, we need to have boundary conditions. So if you recall, we attempt to solve the equation for a string. So let me draw it again here. So this was the string that we tried to solve, and we know no matters how it moves, based on the coordinate that we selected. This one was our coordinate x and the coordinate y. So we know at x equal to 0, y must be equal to 0. So which already the equation gives us that. So it has no use for us. And at x equal to L, we assume the length of this thing to be L. Y also must be 0. So I substitute these things there. YL equal to A sine omega L divided by C equal to 0. So again, A cannot be 0. Sine omega L over C must be 0. In order to set that one to 0, we conclude omega L divided by C must be equal to n pi. And this n can be 0, 1, 2, and so on. So from here I can find omega. So omega will be n pi L multiplied by C, which I already have C, which is T over N. And this N can be equal to 0, 1, 2, and all the way to infinity. So this omega that we found, similar to the single degree of freedom, we refer to them as natural frequency. We will put an index n there to identify which natural frequency we are talking about, because now we have infinite number of natural frequencies. So put these things back to yx, and this yx becomes a sine n pi x divided by L. So since n can change from 0 to infinity, we will put also an index n here, saying that we have infinite number of these yn. Depends on what is the value of n. Right? Because we have an n here in the equations. So similar to what we discussed before, and just some terminologies, we refer to this guy as natural frequencies, and we refer to this one as the mode shapes, which we discussed in details last week on Monday with that string, right? With the string that we played, we saw what happened. So let me remind you again, I draw the string here, and then we will see what we have. So this was our original string. And we say if it moves, it can have different form. Say let's give it like this random vibration. Of course, it's not that big. It's small, but I just exaggerated here. So what we found now is, let's say y. That this string naturally can have the natural frequency of omega 1. We're putting n equal to 1 because n equal to 0 doesn't give us anything but 0. Omega 1 is pi L square of t over m, and y1 smaller file. All right. And y1 is, just look at the equations. A is just a scaling factor. We just skip it for now. It is sine pi x over L, which these things can have, is half a sine, right? And it has this form. Second natural frequency, let's call it omega 2, is 2 pi divided by L Tm, and y2 is sine 2 pi x L. And look at the 2 pi xl, it's a complete sine and has different form. This form. And if you continue with the third mode omega 3 is 3 pi L Tm, y3 is sine 3 pi xl. And you know what the shape will be. And keep going to omega n, whatever n we want it to be. N pi L Tm. Let's put these things like n yn sine n pi x L. Right, and this n can go, as I said, to infinite numbers. So, and here is what I referred last lecture as the really beauty of the math and physics, because you saw with the string that I played, when we plot the natural frequencies, when we did the FFT, you saw we had the harmonic omega 1, then omega 2 was twice as that, omega 3, 3 times of that one. And this is exactly, we will see what we did. We just solved the equations. We followed the physics of the problem. We solved the equations and we ended up to exact same things. So, but we are looking after that green graph, the total response. Right? This is what we want, which is the yxt, the total response. So the total response is sum of all these responses. So my y, x, and t then will be sum of y nx multiplied by cosine omega nt. And if I substitute these values, y, x, and t will be equal to sum of sine pi x L cosine omega nt, and n can be from 0 to infinity. Here is the final response for the string vibration. And we know each of these parameters. We know what is omega n and the rest as well. All right. So as you can see, omega n depends on the tension of the spring. I wanted to give you a second lab experiment, but I thought it's going to be too much work. So in I cancel it. In second experiment, you need a string or maybe an instrument. You play it and you will find the natural frequency by doing FFT. Based on that, obviously, you can find the tension in the spring. Because if you know omega n, simply you can find T, the tension in the spring. So, and as you can see, you can change the natural frequency of this system, the string, by changing the tension in the spring. All right. So, and if we have an A factor here, this is the scaling factor. It depends initially how much we displace the whole things. It can be twice or 3 times, doesn't matter. Okay, so that's the vibration of a string. And the math is easy. So if you review it later, you will see we did just a bunch of derivatives, nothing special. But again, I emphasize a lot on understanding the concept. I want you to understand what exactly happened. Right? So we had a string. This string had mode shapes. Here are the mode shapes, the blue one, the red, the brown, and the pink one. We have infinite number of mode shapes, and those mode shapes are sinusoidal for a string. We cannot argue that this string can have a mode shape. Let's say somebody comes and claims that I can build a string that has this mode shape. Right? It's not possible. Or maybe somebody in future makes something that has this shape. So it's not a mode shape. Or a natural mode shape. Because naturally it's not possible to excite a string and get to this weird shape. Or physically it's not possible to have a mode shape which, let's say, comes, breaks somewhere, go back, go there, and have this form. Because now it is not continuous, right? So these are not the mode shapes of this system or the natural mode shapes, unless somehow we have some external forces, constraint or other things that we get them to those shapes. We're looking after the mode shapes. Those are the mode shapes. There are infinite number of those. And the response of the system is sum of all those mode shapes and frequencies. Now, the question is how many n we should go. Obviously, the more n we have, the more accurate response we get. And when we use, let's say, computer, sometimes maybe if we just use the first 5 or 10 modes, we get to the response that we want. Sometimes we may need to go to the first 50 modes. But most of the problem that I solve, like in practice for continuous system, like usually the first 6, 7 modes gives me an accurate response. Sometimes maybe even 2 or 3 modes, they are good enough after you add them. Right. So again, remember these, we are looking after finding that green graph. Is it green? Yeah, it's green there. So yxt. So that green displacement of the string is sum of all those things, right, which they are vibrating by a frequency of omega n and the shape that we have. We add them up, we'll get to the actual response. How many we need? If we want an accurate response, we need infinite number of these. However, in practice, the first 5, 6, 10, depends on the problem, is good enough. All right. Any question for this part? Oh, good. I hope you understand these wave equations. As I said, these string equation also referred as wave equations. Now, let's get to something more interesting. Vibration of a beam. Now we are adding another dimension. So far, it was just a string. Now we have a beam. Okay, we want to tackle this problem. All right. So like always, we need to start with free body diagrams and driving the equations. We use Euler or Lagrange. That's the tool that we have, or Newton. And let's see what we get. Let's start by a simple beam. Let's say, in general, I have a beam, and for now, I don't identify the boundary conditions. It can be a cantilever beam, it can be fixed, anything. Let's leave it as just a free beam for now. And we will fix the, like let's say the corner, we put our coordinate there. Remember, always we need coordinates. So I'll call this one X and this one Y. These X and Y, they are fixed to the screen. All right. And let's say somehow this beam vibrates. Okay. You can think of vibration of a beam. Let's say if you have a ruler, that ruler can vibrate if you attach it somewhere. So let's exaggerate and say that the center of that beam, like the neutral axis of this beam or the top of it, doesn't matter, gets a different form like that. Some random shape after we excite it, but something reasonable. So I need to do the Newton law, but similar to a string, as you saw on Monday, we cannot do for the whole things. What we need to do, we'll just pick maybe a small portion of that things. Let's exaggerate for now, but this dx is, we assume it is very, very small. So this is dx. Separate this dx. All right. Now I need to draw the free body diagram for this one. So the forces that I have. So you remember from MEC 360, either in the past or if you're having it, when we cross a beam, we have internal loads, right? Similar to a spring, similar to the string, the previous example that you had tension. Here now you have shear force and bending moment, right? So let's say, following the same rules that we have in MEC 360, depends on the left or right side of the dissection. I have V over here, I have V over there, and M here, another M there, right? So if you forget, when we have a beam, at any point when we cross that beam, we do a cross section of that beam. At the cross section, we have internal bending moment, which we show them by M, and internal shear force, which we show them by V. In a static or in MEC 360, left and right, we say they are almost the same because everything stay there, no movement. Like this thing doesn't have to move ups and down or rotate. So the V on the left and right and the M on the left and right, they must be equal. But here it's not, because we have acceleration, right? Like this guy is moving and we have acceleration. Since I have acceleration, the forces, now they are not equal. So if the left is V, I assume by the time I get to right, this one is V plus dV, some changes, which I don't know how much they are, and M is a dm. That's my free body diagram. And this is my acceleration for this mass that I separated. So assuming that this guy has mass per length of mass per length, let's say it is m, therefore the mass of this little element will be dm, portion of that mass, which is m multiplied by dx. Because we said our mass per unit length is m. Not the total mass, mass per unit length or per length. So this is my free body diagram. Do I need to draw the mg, the weight? No, because we say this beam is elastic, similar to a spring. The weight, when it was at equilibrium, was canceled out by some initial deflection. So my free body diagram is complete. All I need to do is writing sum of the force is equal to ma. Obviously, we are talking about direction y. So in direction y, what do I have? I have minus v. I have v plus dv. Those are the forces. Equal to m. My mass here is mdx. And my acceleration, similar to a string, is the second derivative of y with respect to time. Since y is a function of x and t, it depends also on x. I cannot just simply write d2y dt squared, as we discussed before. It's a partial derivative. So we can obviously get rid of these v's. dv. So let's assume that the v change by the rate of derivative of v with x. Then I have to use partial derivative because this v depends on where I am on the beam and depends on the time. And let's say this is the rate of change in shear force. So therefore, my dv here is derivative of v with respect to x multiplied by the amount that it changed during this x transition. As you can see, the equations are exactly, or the process is very similar to the string, but maybe a little bit more details. And on the other side, I will end up with m dx, second derivative of y squared. I can get rid of dx. And what I got here is derivative of v with respect to x is equal to m multiplied by acceleration. That's one equation. What we found is that the change in shear force, V, on this beam has this relation with acceleration. So it means acceleration now, it can change the shear force in this beam. So we dealt with V, now let's deal with M. So for M, I need to write, and remember, this is the Newton law for just linear motion. Now I need to write the Newton law for rotation, or the Euler law. Sum of the M is equal to I alpha. So this I obviously is the, because later we have another I, you don't want to get confused, is the mass moment of inertia. Inertia for this dm, this little element. And alpha is its angular acceleration. So take a look at this little mass m. It moves ups and down. Obviously, for a beam, if it has large deformation, it can also rotate. So it has alpha or theta double dot. We cannot ignore that one. It can somehow rotate. But I is very, very small because dx is very small. So you can think of now a link or a bar that has length dx. Then you need to get it to the power of 2. So it's very small. And what I can do is simply say it is too small to think about it. So the whole things over here will be 0. One good thing, simplify things a little bit. And in fact, it is true, because also if you look at this dm, first of all, the I is very small. Second of all, there is not that much of rotation. So let's take the derivative about maybe left side or right side. I'll go with the right side. Let's call that point of cross section, maybe point O. So sum of the moment about point O is equal to 0. And let's select the positive direction. Doesn't matter which direction will go positive. So I will end up with M. And then I have V multiplied by the distance, which is dx. I have minus M plus dm. And that V plus dV is passed through point O. So it doesn't have any moment there. Equal to 0. Simplify that things. So we'll get rid of M, make sure that I haven't missed anything. So we'll end up with V dx equal to dm. And what I can do, I can do V dx is equal to, instead of dm, I write down derivative of m with respect to x multiplied by dx. How much, similar to v, how much m is changing during this transition dx. So I assume this is the rate of change. I don't know how much it is, but this is the rate of change for m multiplied by dx. I get rid of this dx, and I will have v equal to derivative of m with respect to x, which it should be familiar to you, because in MEC 360 or in the past, when you had a beam, there was a relation between V, shear force, and bending moment, right? Always the derivative of bending moment gives you the shear force. So you saw this relation before in MEC 360. Saw this before in MEC 360. Or maybe if you were somewhere else and you are here as an exchange student, maybe in one of your solid mechanic course. Doesn't matter, we will just use it. But this is a relation acceptable, and you saw we managed to prove it as well outside MEC 360, because now everything is vibrating, moving ups and down. So between V shear force and bending moment at any point, there is this relation. So, but what I need here is derivative of V with respect to X, all right, in the equation above. So what I will do, I'll take the derivative of V with respect to X, and it gives me second derivative of M with respect to X squared. Let's call this one equation 1, and this one, let's call it equation 2. So from equation 1 and 2, I substitute this guy there. I will end up with second derivative of m with respect to x squared, give me m derivative of y with respect to time. So it looks better, but still not enough because we have something that we don't like, and that's m. M is something happening inside the beam. That's the bending moment, but we don't know how much it is, and we don't like to deal with that one. So we need to go back and rely on our previous knowledge in solid mechanics. So we go back to MEC 360 again. In MEC 360, the topic being deflection. We had a relation between m, bending moment, and the deflection of a beam. When I have a beam and it deflects under some load, so you saw that we have this relation. Let me write it down first here, the form that you know. It was like EI multiplied by the second derivative of y with respect to x squared equal to m. So again, if you forget 360, doesn't matter, but just something that we didn't magically bring it up. It is from some previous knowledge. Or if you were somewhere else, you did your MEC 360 or solid mechanics somewhere else, this is an acceptable relation, which we prove it in MEC 360, but not here. For any beam that has modulus of elasticity E, and don't confuse this I. This I is the second moment of area. This beam has a cross section, right? Let's say my beam has this cross section. Just draw it up here. So that's my beam cross section. Cross section. And we know for a beam with a cross section, when it bent about its neutral axis. And it has an I about that neutral axis. For example, for this shape, it is 1/12 BH3. If it is round, it has a different I and so on. So don't confuse this I with other I that we used in this course, right? This is the area moment of inertia. Unlike this I that we use. There was something with those people driving this equation at that time. They just used the letter I and everybody stick with that. Okay, so now in vibration, we use the same formula, except something that we need to be careful. EI is EI. Those are the same. We have the partial derivative. Because now Y also depends, in this course, depends on time. In mechanics of material, everything is static. Nothing is moving. So that's why we simply write the simple derivative. So, and another thing that I need to be careful is the direction of Y. In MEC 360, usually we consider Y to be upward. So I should put a negative somewhere here, although it doesn't matter at the end, but just to be exact, because right now I pick my Y downward. For the sign to work out, I should have a negative sign there. So that's my solid mechanic relation for a beam. So the relation between a bending moment at any point and EI, the module of elasticity, multiplied by the moment of inertia I, and the second derivative of y with respect to x. So, but what I need here, let's look at this equation. Let's call it 3. Equation 3, what I need is second derivative of m with x2. So I need to do the second derivative. From here, I can find out second derivative of m with x2 is equal to EI is constant. It gives me the fourth derivative of y with respect to x4. And let's call this guy equation 4. Oh, I need more room. What were I thinking when I wrote these things? Maybe I was drunk. I thought I can fit the equation of a beam in one page. Let's make some extra pages. Color. Okay. So I'll move this part. We'll talk about it later. So we're getting to this page. Now let's combine all of them together. So combining equation 3 and 4, it gives me, I hope it doesn't give you a headache, but let's see what we get. Minus EI, derivative of 4y with respect to x4, m, second derivative of y with respect to time. Let's order this equation. It will be m, second derivative of y with respect to time, plus EI, derivative of y, x4, equal to 0. And this is the equation for a beam, the final equation. The equation of motion for a beam, like a general formula for a beam. And always, as I explained on Monday, for like what we did with a string, keep saying a string, try to see if there is any analogy between this one and a single degree of freedom system. So in a single degree of freedom system, you had my double dot plus ky equal to 0. Right? If you had only one mass and with a spring, right? So this is the equation. Here somehow I have the same thing. So this is my mass m multiplied by the acceleration y double dot, but acceleration now depends on x. It's not just depends on time, depends on where I am on the beam, this value changes. Then I have a stiffness. The stiffness for a beam is EI, which in again MEC 360, you saw that we call EI the bending strength. Right? It acts something similar to a spring. So it is in fact a stiffness. But the equation works in a way that instead of y, now I have the fourth order. So this is a fourth order PD. So it's not an ODE, it's a PD, which is a lot of fun solving it. Okay, so, but I'm going to pause here and see if, yes, go ahead. If we fix it at one end, both ends, it's going to be a different beam, we can solve it, which we will. No, not similar to a string. Somehow you will see the mode shapes are similar. So Corey is asking if I fix this beam at the two ends, does it behave like a string? So the answer is it behaves like its mode shapes. You will see they are similar, somehow similar, but you will see. But it's a different physics. The natural frequency definitely are different. But somehow we can think of a string as like being a very, very tiny beam. Except with a string, if you notice, we didn't include m, because we said a string cannot handle m. So, any other question?
Where you combine 3 and 4 there, is it supposed to be over dx to the 4? Partial f.
So, question 4.
When you combine 3 and 4,
right?
Negative ei.
Oh, yeah, this is 4. Yeah. Thank you, Ray. X4. Thanks. Yeah, that's 4. Right. So please go back and check these equations later before we solve them. Make sure that you understand what it's a little bit too much. Later, when you check them, you see, in fact, nothing special, but it's important to understand because you may have equation, let's say a system in your exam that I ask you to develop the equations, but for a different system. So you have to know what is the mechanism. Like in SDOF, we learn how to draw the free body diagram. In NDOF, we learn how to draw the free body diagram. Here, also you need to learn how to draw the free body diagram, get to the equation, and then, of course, learn how to solve it, which we'll solve it on Friday. But give it some thought and try to see how you can solve these PDE. Thank you very much.